Hi, so I'm pleased to introduce Russ Taylor. He is a professor and research chair in radio astronomy at the University of Cape Town and the University of the Western Cape. He's also director of the South African Inter-University Institute for Data Astronomy, which is IDEA, or at least I hope that's how it's pronounced. And it's a partnership of three universities to build capacity for turning big data into knowledge on the pathway to the square kilometer array. He graduated with a PhD at the University of British Columbia in 1982 and has been a practicing radio astronomer for over 40 years. He moved to South Africa from the University of Calgary in Canada in 2014 to establish IDEA. Today, he's going to tell us about challenges and innovations in the visualization of radio astronomy data and the CARTA project. So Russ, please take it away.
So I'm going to be talking about challenges and innovation in visualization in radio astronomy. And the challenges arise because of the capabilities of the next generation of radio astronomy interferometers that are currently or soon to be under construction, and the changing mode in which radio astronomy is being done as a scientific enterprise. So the first part of my talk, I'm going to talk about that dynamic. And then in the second part of my talk, I'll talk about some of the work we've been doing to address those challenges by developing new visualization software and approaches. So in South Africa, where the IDEA Institute resides, we are quite connected to the Square Kilometer Array project, which is going to be the large dish array for the Square Kilometer Array is going to be built in South Africa and across Africa. And what you're seeing on this page is a picture of the Meerkat telescope, which is the first phase of that mid-frequency array for the Square Kilometer Array. The work being done with Meerkat really is a foreshadowing of what's coming with the Square Kilometer Array in South Africa. So this diagram shows the growth of data in radio astronomy as a function of time. It's linear on the x-axis and logarithmic on the y-axis. So the straight lines on this are exponential increases in data. And what you see from starts in the year 2000 and goes to 2035. And our current epoch of time is sort of right in the middle of this graph. And you see, for the first decade and a half or so of this century, we had a growth in data from existing facilities as they upgraded their capabilities with broader band correlators and wideband receivers and transmission systems. And that growth in data up to about 2015 or 2018, the doubling time for that growth was about 2 years. So we had a moderate growth of data during that period. But beginning right about now, we're entering a new phase of data growth in radio astronomy with a much steeper slope, and the doubling time for that data sets from these telescopes is more like 8 or 9 months. So we're looking at an era where the volume of data coming from radio telescopes is increasing dramatically. These data sets are visibility data sets, so it's the data that's turned into science products, but it presents the kind of challenge that we're going to be facing processing and analyzing radio astronomy data. What we do with those data, of course, is where the challenge for visualization comes. And you would have noticed in my first slide, I think that many of the next generation facilities, certainly the NGVLA and Meerkat and the SKA, are comprised of a large number of small antennas. And with a small antenna, you get a large field of view. The field of view is given by 1 over the diameter squared, the area of that field of view. And those small antennas are distributed over baselines of hundreds to several hundreds of kilometers, up to thousands of kilometers. So they produce very high resolution images. And a little equation at the bottom of this diagram, the number of voxels that you have in a data set from radio astronomy interferometry goes as the baseline over the diameter of the telescope squared, comes a number of channels. All of these are increasing dramatically. So we're seeing the image data sets coming out of these interferometers growing tremendously. Another way of looking at this is basically we're doing VLBI over the full field of view of the interferometers. This diagram basically shows maximum baseline on the y-axis and and fraction of the field of view that's imaged on the x-axis. Traditional very long baseline interferometry had very long baselines, but imaged only a very small fraction of the field of view. This next generation of facilities and the next generation of science projects will image the full field of view at resolutions which are approaching VLBI resolutions. So they're very large image sets. And in fact, we are now seeing projects where it's not just the field of view of the instrument that's being imaged, but many, many fields of view to create what are called mosaic images over very large areas of the sky. And these produce terapixel scale image sets quite quickly. So that's what's happening in terms of the data sets being produced and the images being produced by interferometers that are currently operating and planned. The other aspect of the change in radio astronomy is the sociology. Because we're moving to a situation where we have individual, single, unique world-scale facilities that are built by a large collaboration of nations. There's only one of them in the world. They have big, ambitious science goals. You have a situation where these projects have identified key science that just justified the construction and spending the money on these facilities. But it's key science that astronomers all over the world wish to be part of. And so the science programs for these facilities, certainly that's true for the SKA, is a small number of key projects which will get thousands of hours of time during the initial phase of the facility. And these are called survey mode programs and get large amounts of time over a period of several years. And these projects are being executed by teams that are distributed all over the world. So we have a very different dynamic in the way the science is done. And that dynamic produces very, very large data sets that want to be worked on by people that are distributed everywhere. And none of them can individually have the data on their desktop. So it's a very different way. And the challenge is to empower doing the science with these big data sets by distributed teams. This is true for the, for the Meerkat telescope. Meerkat will operate for about 5 years before it becomes part of the first phase of the SKA. And during that time, it's doing 8 large projects, which take about 60 to 70% of the time of the telescope, each of them having thousands of hours of observations. And the teams working on these projects are distributed all over the world. They've come from 22 countries and over 100 institutions. So in South Africa, we've approached this problem by building a large cluster and building a dedicated cloud upon that cluster. This is called the LIFU. I won't go into the details of the cloud because that's beyond the scope of this presentation. But there are sort of 4 channels into the cloud facility. And one of them is the visualization platform. And that visualization platform is designed to allow us to visualize these large data sets. So these large data sets, what do they look like? One of the other things the cloud does, of course, is implement pipelines for users to take those large visibility data sets and turn them into images. And basically, there are 3 types of products. There's very broadband, high sensitivity, single plane continuum images. There's 4-dimensional hypercubes, which encode space, frequency, and polarization state. And there are spectral line cubes, which are 3-dimensional structures, 2 dimensions of space and 1 dimension of frequency. Here's an example of one of the high sensitivity broadband continuum images. And you see this image, it's about a little less than a degree across what you're seeing on the screen. And you see on this picture, every signal you see on here is a real source in the sky. Okay. So we're seeing images which are producing data sets that contain tens to hundreds of thousands of sources and occupy areas of several square degrees. So we have this challenge of exploring this n-dimensional universe of big data. Right? The data sets are comprised of large, wide field, high resolution cubes and hypercubes. We also have to address large catalogs of information. As you saw, there were hundreds of thousands of objects in these cubes. So we have to fuse together image data sets with catalog data sets. And we also have to empower teams that are distributed all over the world to work in this data set in a collaborative fashion and to access it for visualization and visual analytics. So, so the challenge then is to visualize these big data sets. And the approach we're taking is implementing solutions for this is CARTA, the cube analysis and rendering tool for astronomy. This project is a collaboration of 4 institutions, Asia I in Taiwan, my institute in South Africa, IDEA, NRAO, and the University of Alberta in Canada, which is part of a national project in Canada called Sarada, which is developing tools for creating and mining value-added data sets in this era of big data and radio astronomy. So what does CARTA bring that allows it to work with big data sets? Well, one of the issues, of course, is the fact that nobody can have the big data, so the data resides somewhere, and it resides, in the case of IDEA, on the Litho cloud. So we have the several terabyte image data sets sitting on a server, but is served to a client, and the client is any web-enabled device that can run client software like WebGL and React and JavaScript, which is pretty much any device these days. So you're separating the handling of the big data from the visualization. What gets sent to the web client is a much smaller set of data sets, which are the data that's being visualized. All the work on turning the data into visualization products happens on the server side. The visualization happens on the client side. So one of the first things we had to address for the big data was the format of the data that sits on the server. We have long in radio astronomy been working with a data set called a FITS format, the flexible image transfer system, which was designed a long time ago, and it was designed as a standard for interoperability and mobility of data sets, to be able to transfer data sets. And a lot of visualization tools have grown up around the FITS format to allow us to look at data sets that are in FITS format. But FITS format has a lot of issues when you're trying to work with big data in high performance. And so at IDEA, we've developed a format for big data, which is based on the HDF5 schema. And here's basically a diagram of the layout of the data format and structure. And there's a publication that you can look at from 2020, which describes this in great detail. A couple of the key aspects of this data set is that it stores the data in 2 forms. Sort of the normal presentation of 2 spatial axes and a frequency axis, but then a rotated version of that, which has the frequency axis on the principal plane, the first principal plane. And that allows us to create data sets which mine the z-axis of the data set quite quickly, Z profiles, regions that are X, Y, and Z. We also sort a tiled version of the data set, basically a MIP-mapped tiled version. And that allows us to access the data quite quickly for sending to the client for visualization. And we also pre-calculate the statistics of the data set, because one of the things that the visualization system needs very quickly is the histogram to decide what the intensity values are going to be in converting from data to intensity. And calculating the histograms for these data sets can take a long time. So they're all pre-calculated and stored with the data format itself. Here's a table showing some of the speedups that you enjoy as a result of working with HDF5 format. Just extracting an YZ slice of data from this data set takes 5 seconds with bits and 2 milliseconds with the HDF5, speed up to over 2,000. Z profile also speed up to several hundreds. I won't dwell on this, but there's a graphic here which shows the speed up for various workloads that you get from this data format, and it's 100 to 1,000 for most of the common workloads. And it makes feasible the ability to image and send data to the visualization client for big data sets. Just an example of loading a 40K by 4K data. You probably didn't notice the time lag there, but click on load, and it's there instantly. So this is serving the client from the server. This is all happening over the internet to a client. And we can load a 6.4 terabyte cube, 40 by 4K by 1000K in about 2 seconds. So it really makes the access to these very large data cube interactive and fast. Okay, so the Carta, the client side sees a web application, and this is a picture of the web application. The web application uses what's called this golden layout, so that the interface is totally configurable by the user, and those configurations can be saved on the server, so that you can reconstruct or revisit workflows that you've been working on, or construct your favorite layout and use that for all of your data. You can interrogate many cubes at the same time. This is an example of 3 cubes being loaded simultaneously. The CO cube from, I believe, ALMA. It's CO2 to 1, the different isotopes, the normal 12 and the 18 isotope, sorry, 12, 13, and 18 isotope. And you can interrogate and match these cubes simultaneously. You can define regions and produce spectra over the cube. I don't have time to go into all of the features and capabilities of Carta, but it's designed to be able to provide a way to analyze data cubes, and not just single cubes, but multiple cubes to do multi-wavelength science. We can also, because all the activity happens on the server, it's very quick to produce moment maps, even for large cubes. It's all done in RAM, and the moment maps are loaded to the client. Here's an example of the cube, the moment 0, moment 1, and moment 2 maps for this. And I mentioned that comparing images with catalog data is one of the important science capabilities. Here's an example of loading a large catalog from a FITS or VO table onto an image. The catalog reader can load 1 million rows in 1 second, and it can render that onto the image in about 2 seconds. So we're not daunted by large catalogs and large data sets. Okay, so I also wanted to talk a little bit about the other project that's under development, which is the virtual reality, doing data sets using VR systems. You'll notice that pretty much all the data sets I talked about are more than 2-dimensional. They're 3-dimensional or 4-dimensional. And we want to be able to image these data sets in their 3-dimensional form. And so we have a software system called I2V, Immersive Data Visualization Interactive Explorer, which allows us to interrogate data sets in virtual reality, either in catalog form or in volumetric form. And we also are working with Planetaria to use the Planetaria domes as a way to project these data sets. So basically, the VR allows you to interact with the data sets not in 2 dimensions, but in 3 dimensions. And you can view these volumetric data sets as three-dimensional structures, and you can impose three-dimensional catalog data on top of it. Right. I'm just going to show a few examples. This is the data set from Meerkat, which is part of the Fornax cluster project. The PI is Paula Sarah from UNAF at Catania. And this is a continuous attracted H1 data cube. And you see that in this cube, there's emission from several galaxies. And you can see the structure, from this very prominent bright galaxy here, which is being enclosed in a three-dimensional space, X and Y, and you can do many things. Again, I'm not going to go over all the things you can do with this, but one thing is you can paint masks. This is a three-dimensional mask, which is initially developed through a shell thresholding process, but you can examine it and you can edit it. You'll see in a moment the editing process, where this tool is doing a subtractive editing, defining his brush, and now using it to remove parts of the mask interactively as he interacts with the three-dimensional structure. You can also do many things. Basically, you have a two-dimensional visualization tool within your three-dimensional reality, and you can define parameters with the three-dimensional structure, which then show up in your two-dimensional representation. Here it's producing a moment one map, and he's interactively changing the threshold and using the mask that he built, and the moment map is being calculated in real time as he adjusts the threshold. So this work is a collaboration between IDEA and ENAF in Catania. We have a team of developers and a team of scientists that are helping develop it and use it for scientific results. And you can also overplot catalogs in the three-dimensional virtual reality as well. This 3D system, this virtual reality system, relies on a dedicated GPU system. So it's not yet cloud enabled. But it doesn't require very much software right now, but except that it's running Windows 10. We plan to expand the operating system capabilities and and cloudify it going forward. So here's some publications if you want to read up more on this. This first publication is quite an extensive paper talking about all of the aspects, both the technical and scientific aspects of the work. And then there's some science results that have used the system. So moving forward, our plan is to blend CARTA and the VR so that we can seamlessly go between our two-dimensional representation on a web client to a virtual reality experience based on selecting data using the CARTA system. So CARTA is, oops, I think I skipped a slide here. Yeah, I just wanted to point out that one of the benefits of the cloud technology as well, that I didn't dwell on, but is the fact that it can go anywhere. You can use it from anywhere because all you need is a web client and a reasonable internet connection. This is an example of a hackathon that we held in the northern tip of Madagascar last year with a bunch of students from all over Africa. And they're sitting in a little cabin using the wireless from a hotel in Madagascar, interacting with and visualizing their big data over their laptops. So it really does empower visualization of data sets anywhere by anyone using pretty much any web device. So just say CARTA is undergoing ongoing development. We are now in the final phases of version 3.0, which is going to have a beta release in April and a final release in June. And we are planning a visioning and planning workshop in February for division what's happening in version 3.0 and beyond. And we have some fairly ambitious goals to begin to bring sort of artificial intelligence into making the system smart and assisting in identifying and visualizing interesting objects, building collaboration tools, building a card for teams, bringing the virtual reality and the web client together. So we have large ambitions. We're going to have a workshop, and there'll be an open invitation if you wish to participate and bring your ideas to the future of visualization of big radio astronomy data sets. You'll be very welcome. That's the end of my talk.
So Russ, I have a question for you.
Is that for Prashant?
Yeah, yes, Russ, that's me.
Hi.
Hi. For the one I'm wondering is, I saw that it was trying to compute things on the fly, but so for the VR headset, it requires. I'm trying to understand what kind of specialized software still it does rely on. It can't be an entirely an open source stack, is it?
The software itself is not open source. It's based on Unity, but it is available on Steam. And you can download the VR IDV from Steam, and all you need on your end is a fairly good GPU in your desktop and a headset that's wired connected to the GPU. So it's like an Oculus Rift system, and a reasonable PC gaming computer will get it for you.
When you're making selections and you're actually making 2D plots live, is it actually transferring data back to Carter and getting it back for the slicing? Because otherwise, it seems like where's the data is still sitting remotely, right?
No, it's not using Carter as a backend. You store your data locally on the desktop.
Okay, so that's what I was trying to get at. So for large data visualizations, you need the data to be locally present. Yeah.
So it's a development plan to incorporate the Carta backend and the VR to bring in the idea is to be able to highlight a region using Carta, pop on your headset and visualize it in 3 dimensions.
Having a third dimension actually opens up new ways in which you actually think about the data itself. So it's very fun to see in that way.
Yeah, it's surprisingly so. When we first began going down this route, I was unsure about what the scientific value of the VR approach would be, but I'm totally convinced now. And Paulo Sierra, who's sort of the project scientist, is quite keen and has produced some real science results that he wouldn't have been able to do without the VR.
Yeah. Particularly actually seeing connections like the case that you showed of galaxies connected to dimensional levels. That was very exciting. Yeah. Do you have a question in the chat? Is it so they're wondering about the data format that would be supported?
The data format for the medical imaging? Is this the question from LA?
Yeah.
Yeah. I don't know much about medical image data sets. We can read in a FITS file into the VR system, and we can read in catalog data in FITS or VO table format.
So it's essentially a multi-dimensional NumPy kind of data set. That's what the medical imaging folks have told us. So it should be easy enough to transfer into a FITS format, right?
Yeah, it should be a very easily solvable problem to convert the data to something that we can read. So there was a question about the exponential data growth chart on the Q&A. So those data sets were visibility data sets out of the correlator. So they are visibility files, which need to be Fourier transformed to create the image data sets.
So most radio astronomy data sets are multidimensional. They're not necessarily only 3 or 4 dimensions. So you can take for visibilities, for example. So is it, how easy is it to switch dimensions? Was my question.
Fairly easy as long as the data format is consistent. In principle, we should be able to visualize visibility data, which I think is what you're asking, because it's basically a 3-dimensional or 4-dimensional data set, like the image, just with different axes. We haven't explicitly designed Carta to do that use case, but it should be fairly trivial to do because the data structure is similar to the images.
I was curious about the VR interface you mentioned briefly. Is this something you expect to be available publicly for like citizen scientists and people like that?
It's available publicly now. The data can be accessed through the Steam. Steam is a repository of virtual reality software that is sort of public domain.
Okay.
So all you need is a system that's sort of appropriate for a PC gaming platform, and you can and a headset, and you can run this software now. As I mentioned, though, our long-term development plan is to put this in the cloud, so that all you would need is a headset and a web device at some point.
So Russ, can you actually elaborate about a little bit more about the script interface, and is it like direct Python hooks, or how is it going to work?
Yeah, it basically is a way to script the API to call Carta functions from Python. So you can embed Python capabilities in a scripting pipeline, or use Carta as a visualization tool from a script. So, but it's currently Python based.
What is the? You show us the development workflow for Carta, but what does it look like for the VR tool? Is it going to be developed continuously for a few years to come, or what's the horizon on that?
Yeah, no, the VR system is also continually being developed. We're just now at the process of redoing our agreement with ENAF for that collaboration. So you can expect bigger and better things on the VR front as well.
Okay, thank you, Russ.